Rotational kinematics is where physics students usually panic, not because it's harder than linear kinematics, but because it looks different. The truth is, rotational kinematics is the same math, but just different symbols. In this video, we'll translate everything you already know about motion in the rotational world and solve some of the hardest physics problems step by step. Alright, so let's start off with what is position and what is velocity and acceleration in the translational versus the rotational world. So as we can see, linearly and rotationally, there will be different variable representations for each. So for position, we have x, velocity, we have v, and acceleration, we have a. Here we have angular acceleration, which is alpha, and that's also represented with rads per second squared, angular velocity, and angular position, which are respectively omega and theta, measured in rad and rad per second. Now, let's look at the formula for angular velocity. Angular velocity is measured as omega and the change of displacement over the change of time. So this is the equivalency to the change of position, which is the change of this displacement over an interval of time. Now, what is angular acceleration? Angular acceleration is the derivative of the velocity function, and that will just be acceleration is equal to delta omega over delta time. Now, let's continue on. So here's a table that represents the linear versus rotational conversion. So as you can see here again, we see linear motion versus rotational motion. We have x for displacement, and v for velocity, a for acceleration, force F, mass m, linear momentum p, kinetic energy 1/2 mv squared, translational equilibrium, Newton's second law as F equals ma, linear impulse as F delta t is equal to delta p, linear work, which is W equals to Fa, and the conservation condition of the net force is equaling to 0. So those rotational equivalencies are theta, omega, torque, alpha, torque, tau, rotational inertia, angular momentum, rotational kinetic energy, 1/2 inertia, omega squared, rotational equilibrium, the rotational second law, which is Newton's second law, just converted with the rotational variance, the analogs, which is tau, which is equal to the moment of inertia times omega, angular impulse, which is the radius times the change in time, which is equal to the angular impulse again, and omega is equal to r times theta. Also, the conservation condition is the sum of the torque externally is equal to 0. Now, down here we have the rotational and the translational link, which is that velocity is equal to the radius times the omega, which is the velocity, the linear velocity is equal to the radius times the angular velocity. So some key ideas that you have to know is that angular motion behaves like linear motion, but just like around a circle. So it's like measuring the same thing, but instead we're looking rotationally around a point, while linearly you're kind of measuring from a fixed point. So this is why, and also you need to know that angular velocity can change without changing direction. And again, remember that a larger radius means that's covered in the same amount of time. In the same time is a larger linear speed, because if it can cover more speed in the same amount of time, it's just going faster. And rotational motion often hides radians in revolutions. Revolutions is not one of the SI units for any of the angular quantities. As you can see here, they are measured in rads per second and rads per second squared. or also equal to radians over seconds. That just simplifies down to that. And that means that if you ever are given something in revolutions, you have to convert rev to radians before you can get your correct answer. So let's start off with a practice problem. So let's say we have a wheel that starts from rest and rotates with a constant angular acceleration. After rotating 3 revolutions, its angular speed is 12 rads per second. Find the angular acceleration. So again, here, the first thing that we do is we convert revolutions to radians, which is, so now we have theta is equal to 3 times 2 pi, which is equal to 6 pi. And now from here, we're going to use a second cake equation. And due to the fact that we are not given time, we have no time. So this is why we use this variant. So essentially it's the third cake equation, but just plugged in with the angular analogous variables. So then we have 12 squared, which is the angular speed, which is equal to 2 times the angular acceleration times 6 pi, which is the theta. Then we just simplify that down, and then we have the angular acceleration is equal to 12 over pi radians per second squared, which makes sense. And whenever you have acceleration, you should always verify that radians per second squared is gonna be your unit that your answer should be reported in. Otherwise, you may have done things, you probably did something wrong. So let's move on to our second question. A wheel of radius 0.5 meters spins with angular speed of 10 radians per second. Find the linear speed of a point on the rim. Okay, so what we're going to have to do, you're going to have to use the rotational link. So we know that v is equal to the angular velocity times r, right? And we can see here that we have a radius here, and then it spins at 10 radians per second, and what we want is a linear speed. What all of these are angular quantities or angular measurements, and what we want is something that's linear. And how do we get between those two? We always use this bridge right here. The v equals angular velocity times radius bridge. So what this means is, well, we can just draw this out just as a quick little note. So it's like moving like this. The radius is 0.5 meters, and it's spinning 10 rads per second as the omega. So we want the linear speed. Yeah, so you're just going to plug in those quantities, and then you really simply, you just have the angular velocity is 5.0 meters per second, keeping the sig phase. And what you need to know is that the angular velocity the angular speed and also the angular velocity in this case, the angular speed is the same because the velocity includes direction. Angular speed is the same everywhere, but the linear speed is not. And you know why? Because at different lengths, at different radii, well, you're gonna be traveling a different linear speed. If you just take the circumference and lay it out as a flat line, you're gonna see that you traveled a different length at the same angle. So at the same angle, there's an infinite number of radii that you could be at when you're rotating around the same angle from something. But that's why there's variation. That's why linear and the angular variation is important to make a distinction between. So let's continue with problem 3. A disk starts with angular velocity of 4 radians per second and accelerates at 2 radians per second squared for 5 seconds. Find the total angular displacement. Okay, so in order to find the angular displacement, we're going to use this kick equation for a rotation. So we have theta is equal to omega initial times time plus 1/2 times the angular acceleration times time squared. So that's going to be plugging in our values. We have 4 times 5 plus 1/2 times 2 times 5. So that's going to give you theta is equal to 20 plus 25, and theta is going to be 45 radians. So what this means, if you want to interpret this, is that large angular displacements are normal. So if you think this is it makes sense because the angular displacement is gonna be pretty large. The radians add up kind of quickly. So some things that you have to remember is that rotational kinematics always mirrors linear kinematics. Always convert revs to radians, and also use the correct cake equation based off the variables you're given. Always remember, like if you're not given time, then don't use something that uses time. Use the correct equation that cancels something out. And remember, cake is constant acceleration, so your angular acceleration has to be constant.